So far we talked about solar cells, but solar cells, for those who do research in solar cells, those who make design solar cells, of course it is of interest to them. As far as we engineers are concerned, who are more concerned about energy, power, we work with modules. So, we will now talk about how do you convert cells to modules. So, these individual solar cells are, you put them in series and then you put them in parallel. So, it is a series and parallel combination of cells which makes strings. Strings is when you put them in series, put them in parallel, you get a module. Okay. And there are concepts like cell mismatching and shadowing. I need to introduce those things. So, typical silicon solar cell has a 0.6 volt nominal. Maximum power point voltage is slightly higher, more like 0.75, 0.8. So, and you can make a string. If you want to do 12 of them, take 20 of them in a string, you will get 12 volt string. But since I told you the maximum power point is at 7.5 volt, so may operate around 15 volts. So, a typical, or you can do 24 volt cell. So, you typically the cells are available in strings or modules are available at 12 volt, 24 volt, 48 volt. They are higher voltage also, but 12, 24, 48 is quite common. 20 will give you a 12, 40 will give you, or you can do 40, 38, you will give you the 24 volt and you will require double of that to get 48 volt. Multiple strings are then connected in parallel to form module or a panel. Now, it is very important, if any cell in a string gets into a shadow, means sunlight is not falling, what will happen? It produces 0 current. So, current will not flow and the whole string goes for a toss. One diode not conducting, the string goes for a toss. So, it may be a 15 volt and certain amount of current, because you have put them in parallel. One diode in a string partially fully shaded will generate that much current. Okay. If a cell is shorted, what happens? Then the voltage, string voltage will go down. Instead of 14 volt, you may get 13 volt. So, but the current will continue to flow. Shorting of a cell does not mean 0 power. The shading on a cell or open circuit means 0 power. Okay. So, the module will not operate in maximum voltage. So, module panels can be connected in series in panel. Again, if you put 24 volt or for a panel and then you put 4 of them, you get 96 volt. You take 48 volt and put 10 of them, you get 480 volts, and typically large voltage and large currents are used. Okay. So, let me see what happens when you connect them in series and parallel. So, here I put 2 cells in series. The current is supposed to flow. Ideally, the same current has to flow. The voltage may be slightly different, should be same, but in reality it may be slightly different. Solars are, if they are not matched, they will be different. So, this is a typical 2 cells, it will be V 1 by V 2, V 2. And so, what will happen to the I V characteristics of each cell was I versus V. Remember that curve that I showed you. Now, 2 of them together will give you, if the 2 currents are same. If the 2 currents are not same, it will give you a lower voltage. Okay. These must be equal. If it is not equal, we will end up in trouble. Of course, voltage can add up. Now, what happens if I put them in parallel? Well, parallel, the 2 currents can be different, and I 1 plus I 2 will come. Voltage has to be now same. So, V T 1 must be equal to V T 2 equal to V T, it will automatically become same. If one of them is at 0.7 volt, other one also will have to become 0.7 volt, or both of them will adjust till common voltage they find. So, this is what happens with one I versus V, voltage is common, now the two of them will ISC1 plus ISC2. Okay. These were OK cells. Now, let us look at this interesting thing, shading effect. Output of cell declines when is shaded by a tree branch. So, this is my normal curve. Now, let me see what happens if I shade. So, if I shade this slightly, the current keeps on falling. I think this is extremely important shading example. It has been taken from this. If you see, unshaded fraction will start giving you current and the shaded one will not give you current. Okay? I think this is a very good example, please take a look at it. So, interconnected solar cells form a solar module. M cells are connected in series, you will get total voltage M into VOC, open circuit, and N cells connected in parallel will give you N into ISC. Module current will be N into I maximum power point, assuming everything is working up, and module voltage will be M into M maximum power point voltage. This is assuming there is no shade, assuming everything is working perfectly. Operating point is called maximum power point. Now, and this is the series and parallel, cells connected in series will increase the voltage and in parallel will increase the current. Together they will give you, if you do 4 cells, 2 in series, 2 in parallel, your curve should have been somewhere like this. And the maximum power will then you will have to calculate. So, this is how whatever voltage and current that you want, you can get several hundred voltage, 1000 voltage, large current, that is how it is made. Now, take example 12 volt 3 ampere cell using 6 volt 1.5 ampere cell. So, I will have to put essentially what I have to do is, this is what I have to do. I have to put 2 in parallel, series here, 2 in series and then in parallel. This is exactly the wiring, same thing. So, you get instead of 6 volt 1.5 ampere which is each panel, you are getting 12 volt 3 ampere. You can make any combination that you want, any voltage and current. Now, a very important thing, mismatch. What happens, the two cells are not exactly the same, similar. They must be from the same manufacturer, pretty much from the same batch. Non-identical cells and shading will impact things. For example, I have already told you output of cells decline when shaded due to a tree branch, building and module dust. Decline in output is proportional to the amount shaded, we already saw that. Now, when they are series connected and mismatch can be due to short circuit current, most drastic power reduction, because total current generated will be limited by the most shaded cell, the worst cell you have to take into account. Open circuit voltage relatively less problem, because that is in series connection, because that much voltage will go down. Okay. Hotspot heating occurs when a large number of shaded cells leads to entire generating capacity of the good cells to be dissipated in shaded cell. So, what happens? There are good cells which are producing and there are bad cells which are not allowing current to flow. All of that energy is getting dissipated there. You will see hot spot developing and you must avoid that. Now, let us take 2 cells which are not identical, that is I have shown 2 different color, and normally voltage will be sum of the 2 voltage, current will be the least of the 2 currents. Now, very important, least of the 2 currents. So, just see, this was one cell, this was another cell. The combination will give you, voltage will give you, but this current will you will never get, you will get something like this, and this is your load line. Suppose you put a resistance, this is your load line. So, you are going to operate here, the 2 cells are going to operate at these 2 points. So, if you see this cell is operating at a very low current. Okay. Now, let me take another load line. Suppose I increase my resistance. Now, this is operating at maximum power point, close to maximum power point, because this is the current that is going to flow. This is operating at another power point. So, this is what you will get, and as load line further increases, you will say this will operate here, not maximum power point, because even though current is maximum, voltage is now gone down. This will operate at this voltage, its current cannot go up, and you will get this peculiar situation. This is extremely critical, combined cell characteristics you must understand. So, this is another example of some unmatched cell. Here what I have done, I have taken 3 modules, one at 16 volt, 15.5 and 15.3. Current is same. So, if you see the power is going to be this multiplied this and this multiplied, same current is flowing. But here let us say current is different. Now, you will have a problem, because you will not see the current, because this will be give you only this will give you this will give you this. You will see that the power goes down. You can't just add this and multiply. Here the current, this will be 46.8, but in series the current is 3.2. So, it is a multiplied. These 3 do not add to this. Okay. All right. So, very important. This is what happens. So, you have to multiply this with 3.2. Here you still can multiply 4.1. Voltage will get added. So, this is an important point, and this is non-identical cells in parallel. Again I have taken non-identical cells, voltage is also different. Voltage will be V1, the lower one, this is the point of operation, short circuit current, this current will flow, plus I1. So, it will actually flow, this will be the load line. So, this will operate at this point, this will operate at this point. If I change the load line, the 2 operating point will be this and this, and if you see, this will operate at this voltage V2, this will, even though load line has changed, this will also operate at V2, this will also operate at V2. Okay. So, the current that will flow is less. Okay. So, cells may act as a sink and shall reduce the effective power produced from the module, reducing the overall efficiency of the module. Sinking cells can become hot and can deteriorate. We already talked about it. There are few important concepts that you must remember. First is the panel efficiency. What is, if there is a power incident, what is the power out? Power out by P in is the efficiency. This is the efficiency, that 16, 17, 18% that talked about. Power in is insolation into area of the panel is going to give you the power in, and P out, this is the efficiency. V max, I max by P in is less than the efficiency of a cell, always less than efficiency of a cell. But if their cells are matched, you more or less will get the same efficiency. So, the other very important point is the effect of temperature. I am now showing this back on a cells, same thing will be applicable to the modules. All cells are defined at 25 degrees centigrade. If you say it goes to the voltage, as you increase the temperature, this curve shifts 25 to 30 to 35, 45, it shifts, at 60 it falls. Now, this is very important. In India, if there is a hot sun, it will operate at higher temperature. So, higher temperature will not give you what was the rated power, it will give you less power. That is the losses that you will get. I know my colleague Anson is struggling, why am I getting less power from a IITM Research Park rooftop? Very often the temperature, and temperature becomes very important corrective factor. This is well understood. There is a short circuit current will fall, will be 30 to 35 milliampere per centimeter square. For every per degree centigrade above 25 degree, it will go up by 0.06 to 0.1%. If you can take 0.1% or even take less 0.07%. So, if it is at 10 degrees, it will 7% reduction, 20 degrees 14% reduction, very important. Same thing happens to voltage. The voltage will change from -2 to +2.3 volt. Now, here I think this is not minus, I think I am making a mistake. We will correct this in the slides. I think 2 to 2.3 millivolt per degree centigrade, VOC will change, and the power as a result will change -4 to -0.5% per degree centigrade. What happens as a result? So, typically say 0.5% per degree centigrade, 5% power will fall for every 10 degree rise in temperature. So, from 25 if you go all the way to 65, you will get a 20% reduction in power. You know, as a result what happens, some of the people where places where it is very hot, they are trying to pass water under the panel. So, the water gets heated, you can of course use also hot water, but as a result the panel remains cool. So, that is what is also done. Of course, somebody else suggested that put it into a canal or something like that, kind of floating. You can do that, except floating panel will never be at the right incidence. So, you will probably lose more power because of incidence. That part is not thought of, because it is politicians who take this decision rather than this. Angle of incidence, essentially you have to face the sun. So, ideally you should move the solar panels as the sun moves from one side to another, and 2 axis tracking, sun may move from north to south, can also tilt, can go on the horizon to all the way. So, 2 axis tracking is you are tracking both moving this direction, moving this direction. 1 axis tracking you pretty much optimize and do only a single movement. But these moving parts introduce failure mode and increases cost like anything. Today the cost of solar panel has decreased so much. You can get 15 to 20% more power by tracking. But if you put it in ideal position, you may still get, I think, so tracking is not used, except sometime, depends, in a place like Chennai for example, south of India, you do not need much. But if it is very much closer to North Pole, seasonal variation at least you may have to do some fixed tracking. So, every 3 months you may adjust the panel once, but in India you do not have to do much. For Chennai you get a certain angle, I think 16 degrees or no, probably 12 or 13 degrees, I am forgetting, and in north your angle has to be slightly more. In fact, in Chennai even if you keep flat, you only lose 1 or 2%. There are other factors impacting the output, age of cells and defects of the cells. As the cells goes up 5 year, 10 year, 15 year, you will see the amount of power it starts producing is less and less. Cell matching, as I told you earlier talked about, does impact. Cable losses you need to take into account, and losses due to connectors, switches and diodes. And then of course, there is a DC to AC. Oh, here it is a tilt given. Chennai should be 11 degrees, Hyderabad should be 18 degrees, Gujarat should be 24 degrees facing south. This is the ideal tilt. Okay? So, I have given that. There is a fill factor concept. Now, what is a fill factor concept? If you see a solar cell operating like this, this pretty much says it is like this and this is the maximum power point, and this is the area that power is produced. This much power is not produced. If you took maximum voltage and maximum current, this should have been the power. Of course, simultaneously it will not happen, but this says what fraction of maximum possible power. You take VOC and ISC and take VMP and IMP, that gives you the fill factor. If you see this cell, in fact, maximum power point the current reduces quite a bit, and the shaded area is smaller than in this case. So, here the efficiency is not, the fill factor is not that good. So, you normally you have to buy power for fill factor of 0.85 are very good cells. Now, why I am pointing out, very often people buy with good efficiency but poor fill factor. So, if you look at it, solar panels, there are a lot of different parameters: open circuit voltage, short circuit current, maximum power voltage, maximum current, maximum power at the maximum power point, the efficiency, fill factor, alpha, beta, gamma. What is alpha, beta, gamma? I will come to that alpha, beta, gamma and L. If you see alpha, beta, gamma are the coefficients for temperature coefficient for power, for current and voltage. So, alpha, beta, gamma. So, L is another important factor. So, you have to maximum power, this is the specification, maximum power, open circuit voltage, this is a 48 volt cell. So, power at maximum voltage is this, short circuit current is this, current corresponding to maximum is 4.04, efficiency here is greater than 15%, positive power tolerance is this, it can get extra power, and these are the thermal coefficient, minus 0.43% per degree centigrade, operating temperature therefore is this, and cells per module and multi-cluster. I am still missing the factor L. So, this is an assignment, please go through it and you will give you. Typical economics, I will just like to very quickly run through the economics. For typically, as I told you, between 1400 to 1600, it is a 17% cell. So, with the right tilt in a good place, this may give you 16.50 kilowatt hour, 1 kilowatt hour panel. Of course, the costs have been falling very rapidly, it is about 20 cent per watt peak today. So, that is what, with 12% losses due to panel, temperature, cables and others, and this is very typical. 1650 will give you 1452 kilowatt hour per year. Now, it is a 1450 kilowatt hour per year and cell cost plus 35% on the balance of system, not just the solar panel. You have to mounting structures, you have to do cables, connectors and converter, AC to DC to AC converter. All of that at, if you do a large installation like 250 megawatt, around 30,000 rupees. Today that is a current cost. Small installation like 1 to 10 kilowatt or even 100 kilowatt may cost you more, closer to 40 rupees. So, this is the typical cost, 30 rupees per kilowatt hour. Now, you assume 10% interest rate and 25 years depreciation and 1% OMC cost, and remember our formula that we had used, depreciation and depreciation and interest combined will give you 3,300 plus 300 rupees. So, your yearly cost is 3,600 and you are going to generate 1450. So, it is around 2 rupee 48 paise per kilowatt hour. That is a typical number. In actual number in India has fallen below this. You are starting to get higher efficiency cell, this was assumed certain efficiency cell, you are getting higher efficiency cell. So, your cost is falling down to 2 rupees. Balance system includes mounting structure, inverter, protections. So, that is what is happening. You are now in India, you can get gigawatt hour, not 250 megawatt or maybe small, gigawatt hour level approximately 2 rupees per kilowatt hour. You have to take into account the land cost also, which is not very significant. So, that is what the economics works out. There is a very interesting thing, can you put solar panel on the oral rooftops called decentralized solar panel, and this will give you 1450 to 1650 watt hours. South facing angle 300 to 325 degrees, and you can calculate cost about 25 rupees per watt peak, and this can give you. I will work on economics and all kinds of things about this later on in the chapter. Seasonal variation, you see this is the peak sun, even in July you do not get, but even there you are getting 4 to 5.25, and this blue color only you are getting less than 4, but even 3.5 is not bad, less than 4 does not mean 2 or 1. This is the typical seasonal variation of insolation. That is what as far as the basic thing on solar.